Swayam Prabha. Digital India. Educated India.
We are going to continue our discussions on gyroscopic motion of rigid bodies. As noted in the previous lecture, we were looking at gyroscopic forces on spinning axisymmetric bodies and precession with and without external moment. And in this lecture, I am also going to introduce the dynamics of a boomerang. Let us directly go to problems. This problem taken from Merriam and Craig. This says a special purpose fan is mounted as shown. The rotor with blades have a combined mass of 2.2 kilogram with radius of gyration of 60 millimeter. The axial position B of the 0.8 kilogram block A can be adjusted. With the fan turned off, the unit is balanced about x axis when B is equal to 180 millimeter. The motor operates at 1725 rpm in the direction shown. Determine the value of B, which will produce a steady precession of 0.2 radian per second about the positive y axis. In other words, we want to have a precession like this. This is the spin of the fan, and because of the weight of this block, we will have a moment about the x axis, which is going to lead to precession. When B is 180 millimeter, the unit is balanced, means the center of mass is at O, then it will be balanced. Let us proceed with this calculation. We will use an approximate analysis in this case. We will assume that the spin of the fan is much higher than the precessional angular velocity, which it is. If you look at the spin angular velocity and the required precessional angular velocity, the spin is much higher than the precessional angular velocity. Therefore, the simplified expression of the angular momentum about that point O is moment of inertia about the axis of symmetry times the spin angular velocity, and it is in the direction of k cap. The whole angular momentum, remember, is now in the direction of k cap. This is consistent with the direction of rotation p. Okay. Now, the moment acting about O is equal to rate of change of angular momentum about O, the temporal rate of change, which is 0 because everything is constant. The only thing that remains is the frame derivatives, and that is angular velocity of the frame cross the angular momentum about O, and this is straightforward. Chi dot j cap, chi dot is the precessional angular speed, chi dot j cap cross I p k cap, and the moment turns out to be in a very simple form, and this moment is produced by what? By shifting the block A, by changing B. If B is 180 millimeter, then there will be no precession because no external moment acts. Therefore, I must change the position of the block A in order to produce this moment. And what will be the moment? This is the shift in the position of the block, because with B equal to 180 millimeter, we have exact balance. If I shift that much is the moment on, and this is the weight of the block that is going to produce the moment, and therefore, this is the expression of moment, and from here I can calculate delta B. On simplification, I get this to be 36 millimeter, 36.4 millimeter, and B was initially at 180 millimeter. Therefore, if I have to add this shift, this I must add, therefore 216.4 millimeter, that will produce this precession. Just to give you a geometric picture of this, this was the angular momentum vector, almost, because psi dot is considered to be negligible. So, this is the net angular momentum. If I produce a moment which is along the positive x, so this is something like a moment vector which I am producing, then as per our equation of motion, h naught dot is equal to the net moment about O, which tells me that the change in the angular momentum about O occurs in the direction of the applied moment. What is the direction of applied moment? This is the direction of applied moment. This is the direction of applied moment. Therefore, the angular momentum must change in this direction. In other words, the angular momentum should shift in this direction, it should rotate in this direction. Let me draw it in the color that I have been using. Therefore, after a small time delta t, I will see the angular momentum rotated in this direction, the direction of applied moment. After another delta t, it is going to rotate further, because this moment, as this x axis is also rotating, as the whole assembly rotates, x axis is also rotating, and the moment direction is along about x axis fixed. Therefore, this whole assembly is going to keep rotating. So, this should give you a geometric idea why providing this moment about x axis, about the x axis which is rotating with the assembly, why providing a moment about this x axis continuously rotates the angular momentum vector. This is a second problem. The housing of an electric motor is freely pivoted about the horizontal x axis, which passes through the center of mass of the rotor. If the rotor is turning at a constant rate p, determine the angular acceleration psi double dot, which will result from the application of a moment m about the vertical shaft if d gamma dt. Now, gamma is this angle which is shown here, is the elevation angle of the axis. D gamma dt is equal to d psi dt is equal to 0 at this instant. The mass of the frame and housing is considered negligible compared to the mass m of the rotor. Take the radius of gyration of the rotor about z axis to be kz and about the x and y axis to be k. This is also a problem from the book of Merriam and Craig. I will use this x y z coordinate system which is fixed to the housing, not to the rotor, but in this x y z frame, the way it has been defined, and we have been defining like this, the moment of inertia tensor is constant, moment of inertia tensor of the rotor is constant. The spin angular velocity p k cap, the omega p, so that is basically because of psi, the change in the precession. So, this is precessional angular velocity because of psi dot, because of psi dot. Suppose there is psi dot, initially actually psi dot is given to be 0, but we will first work through and then we will put psi dot as 0. Now, there is this, you can define this nutational angular velocity gamma dot, the rate of change of gamma, that means this inclination of the axis of symmetry. So, that is gamma dot, the rate of change of inclination of the axis of symmetry. Now, we will put all these things in the angular velocity. First, the frame angular velocity. Frame angular velocity is because of precession and nutation, as we have noted, and the net angular velocity of the rotor is the frame angular velocity plus the spin angular velocity. Therefore, we have the net angular velocity of the rotor. Now, the moment of inertia tensor for this rotor, as we are provided with the radius of gyration kz and k, about the axis of symmetry is kz and about the other two axes is k. This is an axisymmetric rotor. We have the moment of inertia tensor, the other entries are all 0. The angular momentum about g therefore turns out to be this. This is the product of angular moment of inertia tensor and the angular velocity. So, this is the angular momentum about the center of mass of the rotor. Now, rate of change of angular momentum at time t equal to 0 plus. Now, this moment has been applied at time t equal to 0 plus and it has not yet generated any psi dot or generated any gamma dot. Therefore, I find this rate of change of h g following our prescription of course, when gamma dot and psi dot are 0 and this is only at t equal to 0 plus just after the moment is applied. So, this analysis beyond this is valid only at time 0 plus. And we find that the frame angular velocity at 0 plus is 0, and this we have this rate of change of angular momentum at t equal to 0 plus, and this must be equal to the all the moments. Now, the center of mass is sitting right on this axis of rotation. Therefore, it will not produce any moment. The only moment that is generated is because of the applied moment and the moments because of the bearings that I have written in terms of. So, m is the applied moment, represented in x, y, z coordinates. Mx is the moment because of the bearings. So, this is mx, and m prime is about this. This kind of moments will be generated from the foundation, and we have looked at problems in which we have general moments, we do not know them a priori, our equations will tell us what they are. And if I look at the components, I immediately find that moment about x must be 0. This analysis again I mention is at t equal to 0 plus. If gamma starts changing or the assembly starts rotating, then the analysis changes. This is just after the moment m has been applied. First equation, the x I cap equation, tells me that moment about x is 0. The second equation gives me, second and third equations give me these two relations. I have three unknowns: moment about x, psi double dot and m prime, and I have three equations, therefore I can solve, and if I solve I get the angular acceleration about that vertical axis just after the moment capital M is applied. Please remember again, this is valid only at time t equal to 0 plus. As soon as the assembly starts to rotate, gamma starts to change, then the analysis changes. Now, we are going to look at the dynamics of a boomerang. What are boomerangs? Many of you have seen, most of you have seen I think, or you know about it. They are aerodynamically designed tools that returns to the thrower, and these were typically used by the Australians, aborigines, during hunting. If this boomerang, the boomerang is thrown and if it misses the target, then it returns back to the thrower. We can have different shapes of boomerang as shown here: L shaped, 4-armed, 3-armed. I have a boomerang which is a 3-armed one. I will show you a little later. We are going to look at analysis of boomerangs or dynamics of boomerangs. First, we should know what is the structure of a boomerang. I have considered for simplicity this four armed boomerang. So, there is this crossed structure, but these arms have aerofoil shape, and note carefully what is that shape, how it is oriented, how the aerofoil shape is oriented in the boomerang in the four arms. I have also shown an isometric view which makes it clear how the aerofoils are oriented in the boomerang. So, they are all moving in the same direction. The center of mass has been shown by that cross, and the axis of rotation has been shown by this blue line. If the boomerang, if this object is given only a spin about this axis, then this aerofoils will generate lift. Of course, it will generate drag also, but right now I am not I will not consider the drag, I will neglect the drag. I will consider the lift, and that is very important. Because of this aerodynamic aerofoil shape, it will generate lift. If I give pure spin like this, it will generate equal lifts in all the four arms. It will generate equal lifts in all the four arms that I have shown. But if I throw it, I give it a spin and a velocity, then you should note this, that this arm will have a greater velocity, because it is generating velocity because of spin plus v. Therefore, this will have a greater velocity, this will have a smaller velocity, this will have a smaller velocity. Therefore, this is going to generate lower lift. The arm which is at the top in this configuration will generate a higher lift, the arm which is vertically at the bottom will generate a lower lift, because of the combination of the spin and the throw velocity, right. So, because of spin they generate these two velocities, suppose, and because of the throw this will get reinforced, and that generates a higher, that has a higher velocity with respect to the air. Therefore, the lift is higher, whereas the lift in the lower arm is smaller. Other two arms, the horizontal two arms, they will generate similar lift. Now, what happens because of this? There is an overall lift, and in addition there is a moment, as I have shown you. This is the equivalent force at the center of mass of the boomerang. We have the total lift, which is the sum of these four lift forces, and there is a moment because of the moment arm, and different arms are generating different lifts. So, we have an overall moment which I am considering to be roughly vertical. Therefore, we have the angular momentum, roughly angular momentum, because its precessional angular speed that we will just now calculate will be quite low. It will have an angular momentum which is roughly aligned with the spin axis, roughly aligned with the spin axis. It will have the highest angular momentum because of spin. Right. Now, we then look at the effect of this moment. What does this moment, because of difference in lifts in the four arms, what is the effect of this moment? The effect of this moment, so the angular momentum must change in the direction of the applied moment. Therefore, after some time this angular momentum must point in a direction like this, because the moment is acting in this direction, moment is acting in this direction, therefore, angular momentum must change in that direction. As that happens, this boomerang is going to change its course, it is going to change its direction, and it is going to follow, rather than a straight path, it is going to follow a curved path with a certain radius of curvature, and this is the precessional angular velocity of the boomerang. Because of this moment, the angular momentum is going to rotate, and this is going to keep rotating because the face of the boomerang is going to keep rotating, and the moment is fixed to the boomerang. The moment is fixed to the boomerang. To analyze this dynamics, let us make some simplifications. I am going to consider that this effect of lift comes from a disk, because ultimately we have analyzed only axisymmetric bodies. I consider that lift is being generated over a disk shaped object, and which is not a very bad approximation, because the boomerang is spinning at a very high rate and the blades are passing by every point at a very high rate. I consider a small element as I have shown, and I will calculate the lift because of that. So, this is the face on view of the boomerang. I have considered a little element, the area is r d theta dr at an angle theta from the horizontal. So, this is horizontal is the direction in which the moment is fixed to the boomerang, that is the direction of the moment. The little lift that this element generates is 1/2 rho u square C L d A. This is a very standard expression of lift force, 1/2 rho velocity square, velocity of the element square, times lift coefficient. C L is known as the coefficient of lift. C L is known as the coefficient of lift, and this force that you get, actually this force is per unit area. This is how the coefficient of lift is defined. Therefore, multiplying it with the small area of that element, I will get the little lift force from that element. What is the velocity? Velocity of this element is generated because of two things. One is because of the spin, which is omega r, and a component of the translational velocity v, capital V. And what is that component? This angle is theta, so it is the sin theta component. That is the velocity of this element, because of which we are getting the lift. To get the total lift, I integrate this expression, I substitute u in the expression of dl, square it up and multiply it with that dA, which is r d theta dr, and integrate over the whole area of this disk. If I do that, I will get the net lift force on the boomerang. This is acting at the center of mass. This net lift force can be considered to be acting on the center of mass, equivalent force system. Similarly, I can calculate the moment. Now, what I do is I look at the moment arm. The moment arm is, this is the moment arm, which is r sin theta. This is my moment arm, r sin theta. I have multiplied with that force and I have integrated over the area of the disk. Straightforward. When I do this integration, I get the moment expression. These are simple algebraic steps which you can always complete. So, you calculate the lift force and the moment because of that lift force on the boomerang. Therefore, we have calculated L and M. Now, therefore, I have this lift and the moment because of the lift. Now, equations of motion. Newton's second law for the center of mass, mass times acceleration of center of mass must be equal to net force acting on the boomerang. Because I am assuming that it will be moving on a circular path, the only acceleration term is because of the centripetal acceleration of the center of mass of the boomerang, right. Centripetal acceleration mv square by r is the radius of curvature of the path of the center of mass. Therefore, mv square by r must be equal to the lift force, and the other equation is the angular momentum equation, the standard angular momentum equation. I am assuming that there is no angular acceleration of the system, drag etc. has been have been neglected. So, we have only the frame derivative, omega frame cross ig omega is equals to m, and that capital omega is nothing but the precessional angular velocity, which I have shown here. This axis is vertical, this axis is vertical, and this is rotating about this vertical axis. So, that is equals to the moment, and if I substitute all these expressions, I get a relation for omega and v. Now, we know that the velocity with which this boomerang is going to move on that curved path, v must be omega times r. When I do that, I can calculate the expression of r, the radius of curvature of the path, in terms of the parameters of the system, the moment of inertia about the axis of symmetry ig, CL is the lift coefficient which you can find out for the aerodynamic or aerofoil shape of the arms of the boomerang, and rho is here the density of air, and A is the radius of the boomerang. So, we have these three equations which give me velocity, velocities of course, I have thrown it with a certain velocity capital V, it gives me the precessional angular speed and the radius of curvature, and from equations 1 and 3 I can calculate a relation between the spin angular velocity and the velocity of throw. Now, this is where the art of throwing boomerangs come in. When you throw a boomerang, you have to give an appropriate spin and a velocity, so that this analysis or this is the way we understand the dynamics of the boomerang, the way we understand the dynamics of the boomerang, that is satisfied, and it will then follow the path that we have calculated. So, this gives us a relation between the throwing speed and the angular velocity. Now, before I end, I want to show you this boomerang. This is a 3-armed boomerang. I will maybe I will make the screen white. So, here okay, here I have this 3-armed boomerang, and I would like to project it, and it comes back to me. So, this is a toy boomerang, and you can design boomerangs with 4 arms. Designing a boomerang with 4 arms is much simpler, and students typically do it. You can use balsa wood and make a 4-armed boomerang. So, with that I will close this lecture.